We live in a world that depends on perfect digital data. But here's the thing. That data has to travel through a really imperfect, noisy physical world. So how does it survive the trip? Well, today, we're going to pull back the curtain on the invisible mathematical engine that makes it all possible. I mean, really think about it for a second. You dig out an old CD, and it's just a disaster, right? It's covered in scratches and fingerprints, but you put it in the player, and somehow the music comes out completely flawless. How does that even work? It feels like it should be impossible. Or let's take it to an even bigger extreme. A rover on Mars snaps a picture. That digital photo has to travel 200 million miles, flying through all the cosmic radiation and static of deep space. By all rights, it should show up here as a garbled mess. But it doesn't. We get this stunning, crystal clear image. So what's going on here? Is it magic? And it's not just about sending the data over and over again until it gets through. The real secret is this incredibly elegant, powerful set of rules, an invisible mathematical architecture that actually anticipates and repairs damage before we ever even notice it. And this is the best part. The hero of our digital world, the very math that guarantees all this perfection, was once considered totally useless, a purely academic exercise with absolutely no practical value. It's got to be one of the greatest underdog stories in the history of science. So first up, let's talk about math's useless secret weapon. We're going to see how this abstract idea went from a curiosity to the very engine that drives our digital lives. The idea at the heart of all of this is called group theory. And really, at its core, it's just the mathematical study of symmetry. It's a way of defining a set of things and a set of rules that have this perfect, self-contained, and totally predictable structure. But it's funny how much skepticism this idea originally faced. Way back in 1897, a mathematician named William Burnside basically said what a lot of people were thinking. He doubted this whole abstract field would ever lead to anything useful. It was just seen as, math for its own sake. And that is the beautiful irony, isn't it? The very same theory that was dismissed as useless is the exact reason we can piece back together a signal that's been beaten up on its journey from another planet. The abstract structure was just sitting there, waiting for a technology that could finally put it to work. The shift has just been dramatic. What was once seen as a purely academic hobby with no real-world use has become the literal blueprint for all of our digital trust and reliability. It sets the rules that make our data practically invincible. So, how does this actually work? Well, it all boils down to 4 simple but incredibly powerful rules. These are the axioms that guarantee errors can't just be found, but they can be perfectly corrected. Okay, first up is something called closure. All this means is that if you take any 2 things inside your defined set and combine them, the result will always be another thing that's also inside that set. It keeps the whole system self-contained. It guarantees that no matter what math you do to find or fix an error, the answer is always going to be a valid part of the code. No weird outliers. Second, we've got associativity. This rule just says that when you have a bunch of operations to do in a row, it doesn't matter how you group them. The answer is always going to be the same. And this is absolutely crucial because it lets computers perform really complex calculations reliably and super efficiently time and time again. The third rule is identity. So every group has this one special, neutral element. Think of it like the number 0 in addition. Adding it doesn't change anything. In error correction, this identity element represents a state of perfection. When a system checks a piece of data and gets this identity element as the result, it knows with 100% certainty that there are 0 errors. And finally, the 4th axiom, and this one is the real superstar, the inverse. This rule guarantees that for every single element in the group, there is a unique partner that perfectly cancels it out. This is the mathematical undo button. It means any corruption in data can be represented as an error element, and because of this rule, we are absolutely guaranteed to have the exact inverse we need to cancel it out and restore the original perfect data. Put them all together, and you've got this beautiful, complete system. Closure sets the playing field. Associativity gives us reliable tools. Identity defines the goal, a perfect 0-error state. And inverse, well, inverse gives us the power to always get there, guaranteeing that any error is reversible. Okay. But what about really big errors? I mean, the rules we just talked about are fantastic for fixing a single flipped bit here and there. But to handle catastrophic damage, like a deep gash on a DVD, we need to level up the math with something even more powerful: polynomials. These big, messy chunks of consecutive errors have a name. They're called burst errors. And to fight them, we need a much more robust mathematical structure. We have to graduate from a group to something called a Gauss field. So what's the difference? It's really all about power. A group guarantees you can do things like addition and its inverse, subtraction. But a field adds multiplication and its inverse, division, to the mix. And that extra firepower is exactly what's needed to perform the kind of complex algebra it takes to hunt down and fix huge blocks of corrupted data. The codes that use this power are called Reed-Solomon codes, and they basically work like a 4-step diagnostic and repair process. It's brilliant. First, the system calculates a syndrome just to see if an error even exists. If it does, step 2. It uses that result to build a special polynomial. Think of it as a mathematical treasure map that leads right to the errors. Third, by finding the roots of that polynomial, it pinpoints the exact locations of the corruption. And finally, it calculates exactly what the error is and just subtracts it, restoring the message to its perfect original state. So where do we actually see this incredible math in action? Honestly, the answer is pretty much everywhere. This is not just some abstract theory. It is the invisible engine that makes our modern world run. It's in the CDs and Blu-rays in your living room fighting off physical scratches. It's helping the Mars rovers overcome deep space static. It's even working in massive data centers. RAID 6 storage systems use it to completely rebuild all their data, even if 2 entire hard drives fail at the same time. It's in your internet connection too, fighting signal interference. It is everywhere. And the reason all this works so perfectly comes down to precise rules like this one, the Hamming distance formula. Now, you don't need to be able to solve it, but the idea behind it is actually pretty simple. It's a way to mathematically guarantee that every valid piece of code is designed to be very different from every other piece of code. There's space so far apart that even if a few bits get flipped, the system can't possibly confuse it for a different valid message. It just removes all the guesswork. So in the end, this all comes back to one beautiful, elegant idea: the abstract blueprint. We've seen how these core concepts of symmetry and structure, born from abstract math, are the real foundation of our trust in the digital world. It just goes to show you that the useless ideas of yesterday can become the absolutely essential technologies of today, which kind of leaves us with one last big question. If the study of symmetry from over a century ago built the foundation for our entire digital life, what seemingly useless abstract ideas are being explored by mathematicians right now, quietly writing the blueprint for the world of tomorrow?